What I'm going to go through in this video is just recap energy transfers and start talking about where that energy is going. So in this particular picture, what I'm doing is I'm transferring electrical energy into heat. So that is a transfer of energy. Okay, so think about a light bulb. Electrical energy comes in. So electrical comes in, and we want light to come out. The problem is we also get heat. The light bulb actually gets hot. So the heat is things we don't want. We don't want the heat. We do want the light. So that means that not all the energy that we're giving to a system goes where we want it. And how we measure that difference between what we want and what we put in, we give the name efficiency. So that's what we're going to try and look at today. We're going to look at this idea of efficiency. So let's look at the light bulb in a bit more detail. I've got electrical energy going in and I've got heat and light coming out. So the efficiency is actually going to be a ratio. Okay, so the efficiency is the ratio of useful energy that you get out to the total amount of energy that you put in. So, using that definition, let's have a quick look at the light bulb. So this is what I want the light bulb to do. This is the useful energy. This is waste. You don't put a light bulb on to heat up a room. This is the in energy. So if I write this as a ratio, as you know from maths, a ratio is where you divide one number by the other. So the efficiency is equal to the useful energy out divided by the total energy that you put into the system. So you always end up with waste energy. Okay, so when you do this calculation, when you do this, the two numbers it can be between, it has to be somewhere between 0, which means no useful energy has come out, and 1, which means all the energy that you put in has come out. 1 is the maximum theoretical efficiency. You can't get an efficiency equal to that in normal life because normally there's something to do with heat being wasted. Okay, so let's have a look at this example. I've got two different types of light bulb. I've got an incandescent, which means it gives out light by heating, and I've got an LED light, which is something slightly different, and that uses an electrical effect and doesn't get hot. Okay, so the total amount of energy I'm putting into both of them is the same, 300 joules. For the incandescent, I'm getting 45 joules being transferred to light, and I'm getting 225 joules to light from the LED. And the question is asking me, how many times more efficient is the LED lamp? So what we need to do is we need to calculate the efficiency for both lamps. So the efficiency for this lamp is going to be the total amount of energy that you got out as light, which is 45, and the total amount of energy you put in was 300. Okay, so the efficiency for the LED lamp is going to be the energy you got out as light, which in this case is 225, and the energy you put in was the same, 300. So straight away, this one is going to be more efficient than this one because you can't get as big a number doing the actual calculation. Okay, so putting these numbers into calculators, for this one I get 0.15. For this one I get 0.75. Okay, so these are both in decimals. I could actually do them as percentages if I wanted to, because I can work out the percentages and the efficiency as a percentage by just timesing by 100%. So if we do that on both sides, this means that this efficiency is actually going to be 15%, and this efficiency is going to be 75%. Okay, so this is where people lose marks in exams, because what they have a tendency to do is stop. But what we need to do is it's actually asking me how many times more efficient is the LED lamp. So what I need to do is I need to take my 75% and I need to divide it by my 15%. And that gives me the answer of 5. Okay, so this one is 5 times the efficiency of this one, which means for each joule put in to this lamp, you will get 5 times more energy as light than you would in this lamp. Okay, so let's have a quick look at this question. This question is asking me something slightly different in a slightly different way. What it's doing is it's asking me to work out how much useful power you get out. Okay, so this time we need to change the efficiency equation a little bit, because the one I used previously had energy in. But because power and energy are related to each other, what I can do is replace the word energy with the word power. So I can have useful power out divided by total power in. Okay, but it wants me to calculate the power out. So what I'm going to need to do is I'm going to need to rearrange a triangle. Okay, so I'm going to put useful at the top, total near the bottom, and efficiency here. And it wants me to work out the useful power out, which is this one. So the useful power out is going to be equal to the efficiency times the total power in. Okay, so I need the efficiency. The efficiency given to me was 70%. I can't use 70% in the equation, so what I'm going to need to do is convert this 70% into a decimal. The way I do that is I divide by 100. So my answer is going to be 0.7. So the efficiency is 0.7 times by the total power in from the question, which is 800. And that's going to give me an answer of 560. And because I'm talking about power, it's going to be watts. So in this particular case, the efficiency is quite high. So a large proportion of the energy I put in came out. Okay, one thing that people sometimes do by mistake is they actually forget to transfer the efficiency back into a decimal. So let's see what happens then. If I do 70 times 800, what I end up with is I end up with a number that is way bigger than the energy I put in. I end up with 5,600 watts, okay? Which means I'm getting more energy out than I put in. So that cannot be right. So in the exam, if you're asked a question like this, quickly check to make sure that your answer that you're getting isn't stupid compared with what you put in. Because sometimes what you do is you do the calculation, you move on, and you forget that you've done something like a conversion.